Okay, we are going to do section 3.7, which is optimization problems. So we're going to always be finding a max or a min of something. In this case, the first example, a manufacturer wants to design an open box that has a square base and a surface area of 108 square inches. What dimensions of the box will produce a maximum volume? So we need to first draw a picture of whatever we're working with. In this case, we're working on a box. So I'm not always the best at drawing boxes, but let's try. All right. Okay, then we have this back behind. All right, so we have, this is a height of h, and we have a square base, so it's x by x on the side. So the volume of this open box would be the base times height, which is x squared times height. And first we know what the surface area is, which means we need to have the surface area equation as well. That would be the area of the base plus the area of the four sides. Remember, we don't have a top. Okay, so the area of the base is x squared, and the area of the four sides would be 4 times x times h. And we know that the surface area is going to be equal to 108. That was given to us. So something that we're always going to need to do, we're always going to have two different variables. Like in the volume, we have x squared times h. We don't want to have two different variables because that would cause us to have to do a product rule. We need to get the surface area, the x squared plus 4xh equals 108. We want to solve that in terms of h, solve for h, so that we have everything in terms of x's. So h equals 108 minus x squared divided by 4x. And then what you're going to want to do with that is put it back into the volume equation. Since we're trying to maximize the volume, that's the equation that we're essentially going to take the derivative of, because derivatives help us find maxes and mins. So we're going to put the h in for the volume. 108 minus x squared over 4x. Let's simplify that a little bit. 27x minus x cubed over 4 is a simplified version of the volume. So to maximize v, the volume, we need to find the critical numbers. That's always what we need to do. That helps us find the max or mins of volume. So when we take the derivative of volume, it's going to be dv dx dt, because we're in terms of x's for the sides. Dv dx equals 27 minus 3x squared over 4. That's going to be equal to 0 to find those critical points. I'm going to eliminate some of the math on this so we can get straight to the calculus. You get 3x squared equals 108. X equals plus or minus 6. But x is the side of the base, so does it make sense to have a negative 6 for a base? It does not. So 6 is our x. Now our entire question is asking us what the dimensions of the box are going to be. So we know that the base is going to be, we'll put dimensions over here since we have some room. The base is going to be 6 by 6, but we also need to know what the height is, so we're going to put 6 in for the x's here, and our h is going to give us 3 to answer the whole problem. Now what we did is shown right below the guidelines for solving these kind of problems. We identify what's given, what we need to determine, and then we make a sketch, which is what we did. Right, the primary equation, that's the one we're maximizing or minimizing. In that case, we did volume for our maximization, and the secondary equation was the surface area. That was the one they gave us a number in. And in that case, we need to solve for an independent variable. So that was in that last example, x's, we wanted to get rid of all the h's. And then we needed to figure out what made sense. So when we solved for it and got negative 6, we said that didn't make sense, and we only picked the positive one. And then we find the maximum using calculus. Which points on the graph of y equals 4 minus x squared are the closest to the point 0, 2? All right, so here's our equation, 4 minus x squared, 1, 2, 3, 4. We want to know what point is closest. Here's our 0, 2. What points are going to be closest to 0, 2? Here's our xy right there that we want. So if we're trying to find minimum distance, that means we need to use the distance formula, which is the square root of x minus x1, which is 0, plus y minus y1, which is 2. The secondary equation in this case is the one that they gave to us, y equals 4 minus x squared. What we're going to do is plug 4 minus x squared in for y in our distance formula. Okay, when we simplify that out, skipping the math to get straight to the calculus, x to the 4th minus 3x squared plus 4 is what we get underneath our square root. So we need to find the critical numbers of the distance. Well, the critical numbers, we're going to find the critical numbers of the inside because our distance is going to be the smallest when the inside of our square root is the smallest. So that actually makes our problem a heck of a lot easier. If we take the derivative of the inside, it's 4x cubed minus 6x, and then we can find the critical numbers of that. It's actually not too bad of a problem. So set that equal to 0. And pull out a 2x. And you get 2x squared minus 3. And you get 0 and plus or minus square root of 3 halves. So 0 wouldn't make sense for our x value because 0, 2 is our point. So we're obviously not going to use 0. So the 2 points that we want are plus or minus square root of 3 halves. And we know that we're going to use both of them because they would be the same distance away from 0, 2. So we need to put those in for x to find out what the y values are. We get 5 halves both times, which would make sense. We would get the same thing. Finding the minimum area, we have a rectangular page that has 24 square inches of print. The margins at the top and the bottom are 1.5 inches, and the margins on the left and the right are 1 inch. What should the dimensions of the page be so that at least the least amount of paper is used? So we need to draw a picture of this piece of paper to figure out what we know. So we have margins on the top and the bottom that are 1.5 inches. And then we have this distance x in the middle. On top, we have a 1 inch margin on both sides and some distance y in the middle. So the area of the whole entire piece of paper is x plus 3, since we're adding up both of the margins, times y plus 2, adding up the other margins. Since we're trying to minimize the area, this is going to be our primary equation. And if we know that they can contain 24 square inches of print, that's just going to be in the middle here, not including those margins. That's just going to be x times y. This is our secondary equation that we're going to work with first. So we know that we want to work with terms of x's, which is always the one that we prefer. So we're going to solve our secondary equation for y, which would be 24 over x. And then we're going to put that in our primary equation, the area of the entire piece of paper, to solve that one. Okay, I'm going to multiply this out before we take the derivative so we don't have to do the product rule. Always want to try to avoid that. 30 plus 2x. That looks messy. Hold on. plus 2x plus 72 over x is going to be the equation we're going to maximize. And when we think about what makes sense in the problem, we have to have a positive value for our x. So take the derivative, d8 dx, 2 minus 72 over x squared. Set that equal to 0. X squared is 36. So x is plus or minus 6. The negative 6 does not make sense because we need to have a positive x value since it's a piece of paper. So x is 6. We then put the 6 back into the equation we solved for y, and y is 24 divided by 6, which is 4. Now that's not actually the entire answer of paper. What should the dimensions of the page be? We have to add in those margins. So the dimensions are 9 by 6 because we add 3 onto the x value and 2 onto the y value. We'll finish the second half on the second video.